Welcome in Dark Core. The asteroid belt isn't permanent. Between Mars and Jupiter, it's slowly breaking apart, shaped by collisions, pulled by gravity, and fading over time. In this video, we'll explore how scientists measured its slow disappearance, what it means for Earth, and why this discovery is changing how we see one of the solar system's most familiar features. The discovery. The asteroid belt is made up of countless rocky bodies, ranging from dust grains to dwarf planet-sized worlds. While the largest, like Ceres and Vesta, are relatively stable, the smaller and mid-sized bodies are far more active, constantly colliding and fragmenting. This population is where the real story of depletion emerges. Astronomers led by Julio Fernandez from Uruguay's Universidad de la República set out to quantify how much mass the belt is losing. Their approach combined models of orbital dynamics with collisional physics. They found that the collisional portion of the belt is losing about 0.0088% of its material every million years. What happens to this lost mass? Roughly one-fifth is expelled as larger fragments, asteroids and meteoroids that may eventually cross Earth's orbit. Some burn up as meteors, others impact the surface, and a few are tracked today as near-Earth objects. The remaining four-fifths is reduced to fine dust through endless grinding collisions. That dust drifts through the solar system and sustains the zodiacal light, a glow visible in dark skies along the ecliptic. A key driver of this instability is Jupiter. Its immense gravity creates resonances that disrupt orbits, nudging many onto unstable paths. Saturn and Mars contribute as well, but Jupiter's influence dominates, ensuring that the belt continues to lose material rather than settle into equilibrium. This work highlights an important distinction: it is not a fixed relic from 4.6 billion years ago. It is an evolving system, constantly reshaped by gravity and collisions. Even though the present loss rate is slow by human standards, its cumulative effect across billions of years has transformed the belt into a thinner, more fragile structure than it once was. Scientific importance and theories. Why does this matter? Because the asteroid belt's slow disappearance connects directly to Earth's past. Extrapolating the measured rate backward in time, astronomers estimate that about 3.5 billion years ago, the belt was roughly 50% more massive than today. The loss rate would also have been about twice as high. This matches the geological record. The Moon's heavily cratered surface and ancient impact signatures on Earth both point to a period of intense bombardment. It was the reservoir feeding those impacts. As the belt shed mass, the rate of impacts gradually declined. That shift helped create the more stable conditions in which life eventually emerged on Earth. The correlation between the belt's depletion and the declining bombardment rate strengthens the link between astrophysical models and geological evidence. This discovery also ties into larger theories of planetary dynamics. Jupiter's gravity has always been central, but the situation was even more dramatic in the past. Models such as the NICE model suggest that the early migration of Jupiter and Saturn may have destabilized the belt even more, ejecting vast amounts of material. The current depletion rate can therefore be seen as the long tail of a much more violent past. Understanding the belt's evolution also clarifies the origin of near-Earth objects today. Many of the tracked objects in Earth's neighborhood can be traced back to resonances in the belt. The measured depletion rate explains how that supply is sustained. The study reinforces a picture of the solar system as an interconnected system. It is not isolated, it is linked to the history of planetary migration, to the cratering records on the Moon and Earth, and to the ongoing stream of objects that still threaten our planet. Implications and what's next? The immediate implication is for impact risk. Even though it is far less massive than it once was, it still sends material inward. The roughly 20% of lost mass that escapes as debris contributes directly to the population of near-Earth objects. While the overall flux is now relatively low, it is continuous, and understanding its rate helps refine predictions of the supply of potentially hazardous asteroids. The study also explains why the zodiacal cloud remains visible today. Without constant replenishment from collisional grinding, the dust would disperse. Its persistence is direct evidence that the belt is actively eroding. Observing the brightness and distribution of the zodiacal light gives astronomers another way to cross-check models of its depletion. For planetary scientists, the ability to project the belt's mass backward in time provides a valuable tool. It allows researchers to compare model predictions with cratering records across multiple worlds. The consistency between the two strengthens confidence in both. It also opens the possibility of applying similar methods to debris belts around other stars, offering a way to compare our solar system with extrasolar systems. This research has practical value as well. Agencies like NASA's Planetary Defense Coordination Office rely on accurate models of near-Earth object supply. Missions such as OSIRIS-IX, which sampled Bennu, and DART, which tested deflection strategies, operate within the context of this broader understanding. Knowing that it is a living source of new asteroids reinforces the importance of sustained monitoring and preparedness. Its slow erosion links Earth's past bombardment, today's impact risks, and the evolution of planetary systems, a reminder that nothing in the cosmos is truly permanent. Outro. The asteroid belt isn't stable. It's slowly disappearing under the pull of gravity and constant collisions. For Earth, it explains both our violent past and the steady trickle of impact risks today. Far from a backdrop, it's an active player in shaping planets and dust clouds alike. Understanding this process brings us closer to knowing how planetary systems evolve and why it matters for our future. Stay tuned as we explore what this means for us. Thanks for watching Dark Core.